Good morning. This is it's part one of the operational session during the Apricot, and I'm Yoshinobu Matsuzaki, co-chair of the Apops. And before beginning this session, let me announce about lightning talk. We have a lightning talk session on Thursday afternoon, so it's like a 5-minute talk. If you have any idea or something to share during this conference, please submit your slides by using our website, apricot.net. So, given that, let's start the session. First up is Jeff. Are you ready? Feeling good after? And this is your clicker.
This is my clicker.
Yes, and mic.
Oh, and my microphone. I've been told I have 28 minutes. Cool.
And you need to speak slowly because we have an international participant here.
And I need to speak slowly. Those two are mutually incompatible. Hi, my name is Jeff Houston. I'm the chief scientist with APNIC, and I'm going to talk today for 26 minutes, allowing you 2 minutes for questions about routing and BGP. Advance the slide, please. Thank you. That's what I'm going to talk about. So let's start straight away into a foray into IPv4. Next. So I've been doing a snapshot of the routing system every 2 hours since 1996. And oddly enough, so is a really cool project, which has had generous funding from the National Science Foundation at the University of Oregon, called Route Views. So it's not just me, it's a bunch of other folk. And this is the aggregate collection of that entire data. I'm not sure if it's a petabyte, but it's certainly a whole heap of terabytes. And this is the size of the V4 routing table from everybody over that period. Who's playing with my slides? Stop it. I've only got 24 minutes. Keep going. Bring it back, please. One of the features you need to understand is that this slide and this picture shows a fundamental contradiction. The job of the routing system is to give everybody the same information as fast as possible. So if it's the same information, you shouldn't see lots and lots of little lines where everyone sees a slightly different routing table. Should be one line. Because there's basically one default free zone. And your theory and my theory is when I announce a route into the routing system, everyone learns it sooner or later, and sooner or later being in about 70 seconds. But that's actually not the case. And if you look at the top right, whatever it is, you actually notice that that divergence in the last few years is getting bigger, not smaller. Not everybody sees the same routing table, which I find fascinating. The other thing about the routing table is that it is a history of the internet. The introduction of classless interdomain routing in 1994, because obviously we're all going to die. You can hardly see it. The great boom and bust of the 2000s. 2005 DSL to the masses, 2011 address exhaustion in V4. Nobody noticed. Nobody. The great cataclysmic event, we all had to run V6. V4 just kept on growing and growing and growing. This is the last 12 months in astonishing detail. This is every hour for 365 days. And you know, the one feature about all of this is, again, when you really look at it close, everybody sees the same thing, but different. In other words, the big effects are there, but you have more routes than me, etc., across almost every single peer. And of course, those trailers and outliers, someone exceeded their fib limit. the router went, oh, I can't do any more routes, and kind of died off. That happens. So the detailed view doesn't actually expose any major anomalies, apart from the fact not everybody sees the same thing. Slight downtick in March, and at the end of the year, about an 80,000 entry out of just getting close to 1 million entries. So I started to think about, well, what are you guys meant to be doing now? Because there is no V4 left in the registries, is there? You ran out of this. Over the years, we've exhausted it. Now, the theory was that if we could trade addresses on a market, then addresses were worth money. And if you had some unused addresses somewhere in your back pocket, at the right price, you would bring them to market. And we'd take all those unused addresses, and there were a lot, and we'd actually bring them back because they were worth money, and leaving them in your back pocket wasn't making anyone money. And so we kind of thought that the unadvertised address pool would shrink year by year. At around $40 an address, which is what the current price is, the unadvertised address address pool rose by a total of 9.5 million addresses over the year. So the price is not high enough to flush them out. What price would flush them out? Well, $10,000 an address probably would. $1,000 an address? Yeah. But $45, $50 an address? No. Rose by 10 million. It's not high enough. There's still some addresses left in the RIRs. Very, very slight. The last /8 policies, etc. We got rid of 1.5 million addresses out there. And what that meant, oddly enough, is the size of the advertised pool in routing actually shrank by 8 million addresses. Actually shrank. Which actually says something, because we sold a whole lot more mobile phones. We did a whole lot more IoT. We did a whole lot more of more and more, but our aggregate address needs shrank. What does that say about the way we use addresses in this nattered world of V4? The answer is it says a lot. It says a huge amount. Devices don't need addresses anymore. So these counts are not counting devices. They're actually counting more and more conversations, not endpoints. And the conversation rate is not that high, which is why those numbers are shrinking. So I just said all that. What happened? It's slowing down. Peak growth has finished. We peaked at 944,000. It's not going to get much bigger. We only added another 36,000. Autonomous systems, lower, 1,400 over the year. And transit relationships haven't changed. So in some ways, it's the same stuff. Let's move there to V6. So you kind of go, well, everyone's doing V6, aren't they? Well, yes. Here's a comparable view, but not 1994. There was no V6 in 1994. There really wasn't. The data that I have starts in 2004. And you can see way down there in 2011, we ran out of V4 addresses and we're all going to go to V6, weren't we? Just there. Yeah, right. You weren't watching, you weren't listening, you didn't care. The V6 pace has only really gone up in the last kind of 3 to 5 years, January 2018. And then fascinatingly, because this was all quite a solid line, everyone saw the same routing system, but now everyone doesn't. They don't see the same fib. And you almost get a very similar picture to V4, higher slope, and some discontinuities are evident, but see that range? Everyone's doing weird things that they were doing in V4 and V6. Maybe that's a sign of maturity. So overall, 35,000 entries a year, getting up to V4. You're all polluting the space with /48s. How big would your router need to be if we filled up your network with /48s, 2 to the 48th of them? We don't have the silicon. Why is a /48 acceptable as a globally routed prefix? That's an open question. If someone has an answer, Tell me, because I'm keen to know too, because this is just wanton routing vandalism. Because the routing table is not actually growing so much as the more specifics. So yes, more people are using V6, but more people are using V6 with more specifics, which makes your fib table grow like crazy. 60% of all the entries in your routing table are more specifics. I'm running a big router. I need to shovel hundreds of millions of packets per second through that router. I need to look up a routing table for every packet. This is the most expensive memory in your router. And a lot of you are polluting it and making the cost of speed higher than it need be. Because 60% of those routes that are sitting inside the V6 network don't help. They don't extend reachability. It's already announced in the aggregates. But the same problem that we had years ago in V4 with more specifics has reproduced in V6. So that's just what I said. How big is it going to get? How much time have I got left? Is anyone keeping track? How many? 15, 16. Okay. So this is the way the V4 network works. So this is the projection of how big a router you're going to need in V4. This is what used to be. But look at that curve, because the best fit curve is actually a polynomial, order 2, and it's getting down to 0 growth. By around 2028, the numbers say peak V4. No more. We'll have given up growing the V4 network. Now, I don't know if that's true in reality, but those numbers are actually really interesting. This curve is now plateauing, and that's the end of the V4 network growth. Now, the folk who said V6 is the answer should be singing and dancing for glee. This is the day you were waiting for. This is basically V4 has peaked, there's nothing left. Are you getting that message, Sander? Yes, you are, you're smiling. But you see what I'm sort of saying? The numbers from the last 5 years are actually now plotting this curve that isn't even linear. There's nothing left in V4, and the expansion of that network is actually a lot smaller and getting smaller every year. So yeah, I just said that. V6, the opposite. I don't know if any of you are older than me, but we used to tell ourselves the network doubled every year, and that's an exponential growth trend. So this kind of curve you're seeing here is the curve we used to say to ourselves in 1989, 1990, 91. This stuff is just out of control and we've really got a problem. Oddly enough, V6 is still plausibly growing at an exponential rate. Early days, small amount of data, but if it truly is exponential, we're up to 1.4 million entries in the routing table in about 6 years. Is it linear? Look at those numbers, probably not. More likely around exponential. So that's the likely trend in V6, doubling about every 2 years. Still, there's a lot of V6 activity, but a lot of that size is you guys doing routing vandalism with more specifics. So, our fate is in your hands. Oops. Absolute size, growing faster. And don't forget, in your router, we route on all 128 bits, even if you don't use them. What that means is that V6 entries take 4 times the size in the most expensive memory on the planet. So this is the number you should worry about in terms of the size and cost inside your line cards. Is it higher than Moore's Law? Moore's Law is still delivering. There's no reason to lose sleep so far. If we stop making ever smaller, ever faster chips, we've all got a problem. When will that happen? Well, we know it when it's happened. Can we predict that? Not really. They still keep on just dropping down the track width size. And although the clocks haven't changed much for years, more parallelism, we tend to get out of it. But it's not the size, it's what you do with it. What are you doing with updates? I've always found this graph totally bizarre. It's the number of updates per day for, about 8 years. The bottom line is the number of withdraws. And although the network has grown like crazy, the number of withdrawals has not until this year. Why are withdrawals scale free? What's the good behavior churn that stops our CPUs dying? Why is doing BGP actually a walk in the park, even though we're now up to 1 million entries? The number of withdrawals is tiny. And that's the same in your router as mine. The number of updates, again, odd. We've gone through state phases. For the first few years, up to about 2014, it didn't change. Number of updates was stable. Don't know why. It rose, but stabilized. It rose, but stabilized. It dropped, and only in the last few months has it become unstable again. If anyone knows what we are doing to them ourselves, I'd love to know, because I can't explain that. I've never heard anyone else explain it either, why this is still roughly bounded. So surprisingly stable. Inside all of that, withdrawals are stable. It's kind of doing all right. How many prefixes are noisy per day? Almost none for the last 15 years. So the folk who are doing all that noise, I'm going backwards here. The folk who are doing all that noise, very few. Most of the time, most of what you're processing is a small number of naughty people, not a large number of folk doing a few updates. Unstable prefixes are relatively stable. But the really, really good news, the job of routing is to give you new routes and converge. We've gone to 1 million routes, but we still get convergence inside 50 seconds. And we've been inside that since 2009. Pat yourselves on the back, that's an amazing feat. I don't know how anyone did it. Distance vector protocols aren't meant to behave so nicely. This is anti-gravity in action. Well done, everybody. So yeah, brilliant. So V4 is stable, we don't know why. That's a problem because we don't know what will make it unstable, but it is stable, yay. V6, completely different picture. The number of withdrawals is increasing, that's a logarithmic scale, but it's increasing directly in proportionate to the number of entries. V6 is different. It's the same topology, it's the same routing protocol, but the prefix behavior is different. If anybody knows why, they can either tell me or get a PhD. I don't care which, but we don't know. We really don't know why these two differ so dramatically. And the number of updates per day, the green line, is actually increasing with the size of the V6 routing table. Nobody knows why. So V6 is actually noisier. There's actually more churn going on, up and down. That's kind of weird. Number of unstable prefixes, V4 it was rock steady, V6 it's going up. There's another PhD. I don't know why, no one knows why, but on the same topology, with the same routing protocol, V6 is behaving radically differently over a long-term trend. As we scale, we actually see more noise in the system. Interesting. Convergence, V4, rock steady, 50 seconds forever. V6, meh. The time to converge on average day by day has been everywhere from really low in 2018, unbelievably low, up to, 5 minutes, where the thing is just thumping around the network going, better path, better path, better path. Why is that going on? Again, it's part of this issue of why is V6 so different? Not sure why. Yeah. There is a clue, and that is the V6 network is slowly getting better, right? Slowly. If we look at the number of updates against ASs, only a very small number of ASs are phenomenally unstable. And that's the problem. The folk who really emit noise emit amazing amounts of noise. 2 ASs generated 70% of the BGP update load in the last 2 weeks of 2022. If those two stopped, this network would be really good. It would be really, really stable. So a small number of players contribute an extraordinary amount of instability into the system. So Will your routers keep on working next year? Yeah, of course they will. Do you need to do something over 5 years? Yes, for V6, not for V4. What you're doing in V4 will keep on going. It's the V6 component of your dual stack that's actually going to cause you some headaches. Instability is arising because nobody cares. And there's a very small number of folk that if we quietly took them out the back and snipped the wire, you'd actually get a really clean network. And we know who they are. We know. They're even on a web page, so it must be true. So hardware suppliers, the game hasn't finished. Higher fiber speeds, more packets per second, and more routing means actually more hardware in every dimension. So over 5 years, the gear you're running now is probably not going to run line speeds in 5 years' time, but that's always been the case and nothing's changing. So what can I say to you? Know your limits and know your fib card capacity. Know them and make sure you're ahead of them. Because once you start dropping routes, everyone gets angry at you, particularly if you drop Google's routes, because no one will like you then. None of your customers will like you. Make sure you do that proportional setting, because most of these routers go so much for V4, so much for V6. Keep your V6 sort of being looked at and monitored, because if you get that wrong, you're dropping routes, because a whole lot of folk are now prefing V6 because of happy eyeballs. You don't need to route a full routing table. You really, really, really don't. Just aim default at Google and everything will be nice. Aside from that, default is your friend. Default keeps scale out of the problem. And I suspect we're going to start doing hot caching. Instead of trying to put the entire routing table into a line card, you put the top 500 routes. Why? Because 99.99999% of your packets are going to about 5 routes. Put that in your line card and put everything else in the slow path. Nobody will notice. And I suspect that will be a feature of systems as we keep on growing the routing table. So those are 4 practical suggestions about what to do. The last one's for vendors. Are you paying attention? You can make routing cheaper if you stop pushing everything into your line cards. And that's it. I think I'm on time. Questions?
Thank you very much. Any questions? We have a mic in the middle. So if you have any question and comment, yeah, please line up, stand up.
Hi, Jeff. Sandal Stefan, 6Connect. So you said that people are seeing different views of the routing table. Are those differences in the more specifics, or is there actually space that's not being covered?
Oh, both. Absolutely both. And I've done a number of projects to actually understand who can't see whom. And I think Randy Bush did some work about, are they covered by implicit defaults? But it is true, some of this stuff is, I can't see you with a specific route or with an aggregate. I just can't see you. How many folk send packets to each other as distinct from dragging video streaming from Netflix and Amazon? And the answer is vanishingly small. It's a problem, but it's more of an obsessive compulsive problem because users don't talk to other users anymore because this is 2023. So yeah.
Thank you.
Thanks.
Before asking a question, please state your name, please.
Hey, Jeff, it's Matthew Bowcroft here from Imperva. Just curiously, through you talking about the fib, and mostly when you shove stuff into a line card, you don't actually shove the whole fib in. Is it worth, because what you do some compression on it and you look at what actually is usable, because you might throw away more specifics because you don't need them, and so on. Is it worth doing a little bit of analysis of kind of an estimation of what the rib size is growing? Because that's kind of the actual interesting thing. The fib is the fib is noisy and it's got all this crap in it. But
there have been a number of really good research papers. And if you actually look, there are 1 million entries and your router has 20 interfaces. And you can actually compress the entire routing information base because there's only one of 20 decisions. And you could squish all this down to a tiny decision table. True.
Yeah.
But the next update that announces a more specific, you've got to redo the entire algorithm. Sorry, packets, I'll be back in 5 minutes for the new compressed rib. And this entire issue is actually still the realm of a lot of research and very little production equipment. We are still brute forcing our routers. Simple, wasteful, and large works, and we know it works. Smarter and smaller, we tend to doubt that we're smart enough to make it work still. So yeah, it's a really good idea, but it's a hard one to implement.
I guess I'd sort of say, are you sure it's not implemented? And
Sorry,
are you sure it's not implemented? Isn't actually getting your RIB update into your from your CPU into your line card, that often is a bit of a complex and time-consuming process anyway. So doing some compression on it often is useful, just to be able to make that
we need
work
another
better.
talk from Arista or Cisco or something to talk about this architecture. The last talks I've seen over the years is still brute force, just ram it down.
Okay.
It's wasteful. It's the whole reason why we actually route 128 bits of V6, and there's not a single 128 prefix out there. We tend to go simple works, even if it consumes a whole bunch of memory, it just works. So we're not confident enough that we can be cleverer yet. But the numbers are saying you really need to do this better.
Sure.
Yeah.
Okay. I maybe
Either that or use default like crazy.
One thing that'd be interesting for next time you do the talk is now you've got the two different curves happening for V4 and V6 growth. It'd be interesting to like produce a single graph with them overlaid with two different y-axes, because that would actually be interesting to see where that date of change of slope and change of rate happens.
Oh, that's the change of rate has happened some time back.
Oh, sure. But it'd just be interesting to see that as a single graph. That's all.
What's going on, of course, is that if you actually look at the number of networks supporting V6, there's a bunch that don't, which are actually larger than the ones that do still.
Sure.
And it's the pressure of pricing in V4 that I think is driving that, plus just the logistics of keeping the V4 balloon up in the air.
The graph and sort of a line in there of V6 take up, wherever you get that from, would be an interesting single view.
Oh, yeah.
That's all.
Thank you.
Any other question? I have a question. Oh, so default is your friend, but do you think flap dampening is also useful to reduce some amount of update and noises?
I don't think flap dampening is useful if you've only got approximately 10 points of routing instability origination. I think taking them out the back and dealing with them is a lot better than all of us deploying flap damping, because the exercises when we've all deployed flap damping is that we actually penalize good routes that have got minor instability. We've never yet found a formula for everyone does route flap damping and it works. And we've tried for 25 years. Whereas we know who they are, we know where they are, and we know which prefixes are flapping, and it's on a web page. Just take them out and everyone will be happier. You've been warned.
Thank you very much.
Thank you.
So I have a small gift for you.
Oh, thank you very much.
Thank you very much.
Thank you.
Thank you. So next up is Shishio-san talking about port capacity in the future. So
ありがとうございます。
30分で。
My name is Shishu Tsuchiya, SE lead of Arista Network Japan. My presentation title is Merchant Silicon 800 Gig 1.6 Tbps Adoption Projection. And subtitle is Golden Age of Networking Driven by the Moore's Law. Moore's Law, this is copy and paste from Wikipedia of Moore's Law. Gordon Moore is the founder of Intel, who in the 1965 posited doubling every year in the number of components per integrated circuit, and projected the rate of growth will be continued at least another decade. In 1975, looking forward to the next decade, he revised the forecast to a doubling every 2 years. His prediction held since 1975 and has since become known as a law. This is actual result of Moore's Law, 1971 to 2025. 100 million for the improvement over the period of 55 years from 2,300 to 250 billion transistors. This is semiconductor technology, semiconductor technology evolution and roadmap. And the semiconductor technology is evolving, and the switch chip will follow the evolution of a CPU chips. 10 years ago, switching silicon was quite behind because it used 6.5 nanometer technology compared with 49 nanometer technology on the CPU chip. But now they are developing with the latest technology like 7 nanometer. Merchant silicon is sometimes called system on chip. SOC capacity is determined by the SerDes speed, serialization and deserialization, which means electric interface between the switching chip and the optics. The number of lanes a chip can support. Moore's law, doubling every 2 years to the network. This is a long list of merchant silicon, merchant switching silicon first. 2008, first ultra low latency 24-port 10G single chip. And 2010, first large buffer 10G chip with virtual out queuing fabric. In the 2018, first 32 400 gig single chip. And the 2021, the first 64-port 400 gig single chip. This article described about 10 prediction of the networking and Moore's law from Andy Bechtolsheim, who is founder of Alice Network. And he is also said, we are in the golden age of networking, driving by the Moore's law. Library Tech Professor Conference in the 2012. My subtitle, my presentation subtitle comes from this, his comment. This is comparison of a type of merchant silicon, which made by the Broadcom. Broadcom has 3 types of chipset. One is XG Strident, which are rich, and it will be used Leaf and TOR and Campus, and the Tomahawk for the highest bandwidth for the sparring of the data center switches, and the cloud grade scale, DNX Jericho, which has a deep buffer, and for the storage, Hadoop or routing network. Capacity of each of family increased double per 2 years. Tomahawk is targeting highest bandwidth chipset, so it will be the first platform for the newest interface, like 800 gig and 1.6 terabps. This is a powerful 400 gig transfer move from conventional NRZ, non-return to zero to a PAM4. Transmitted as a pulse signal with 4 voltage level of 01, 1011, and 00. So PAM4 can support highest bandwidth, but IDIable is complex compared with the NRZ transfer. This is a 400 gig platform, which use 7 nanometer technology. Tomahawk 3 is 16 nanometer technology, but as I already described, I already mentioned, it is a newest bandwidth, a newest interface supported, and it can support 32 by 400 gig. And Trident 4 is 7 nanometer technology, is for leaf data center switch is 30 to 40, 400 gig. And also Jericho 2C is using a 7 nanometer technology. It for storage and internet routing. And most of the vendor also release modular system by the single chip. So 400 gig interface product expanded to the various fields like leaf or storage or internet routing. This is the Powerful interface. Legacy 100 gig optics electric interface is 4x25 energy, and also optical wavelength is 4x24 energy. In the 400 gig optics electric interface 8x55 power, and optical wavelength wave is 8 by the 55 power, like 400 gig SR8 and the 2A4. And also we have 400 gig DR4 and the FR4, and it uses gearbox technology, which is convert 8 by 55 to the 4 by 100 gig. And 100 gig DR and 100 gig FR optics module that can accommodate existing 100 gig systems, taking full advantage of 400 gig, and now shipping it to use gearbox technology 4x25 energy to the 100 gig power. We have a breakout. There is a breakout option. 100 gig QSFP from 400 gig. If legacy system support 100 gig DR, then we can use 400 gig DR4. And if the system only support 100 gig SR4, then we can use 400 gig SR8 to buy a 100 gig mode configure. This is the CMOS processor node through the 2025. TSMC, Intel, and Samsung has already has a roadmap to the 2 nanometer and 1.8 nanometer technology. And in today is 3 nanometer technology used, and 2 nanometer technology will become in the 2025. This is merchant single chip switch silicon through the 2028. Today is, I already mentioned that today is 7 nanometer technology use. And in the 2023, 5 nanometer technology will be released. And in the 2025, 3 nanometer technology will be released in the switching silicon. This is the bandwidth shipped by the switching silicon SerDes speed, 100 gig SerDes, blue ramping in the 2024, and dominating bandwidth shipped in the 2028. And the SerDes, 100 SerDes, green is ramping in the 2026. This is the switching silicon capacity density. In the 2022, in single chip, 25.6 BPS capacity has, and it uses 7 nanometer processing technology, and it supports 400 gig optics. And in 2024, it will be released 51.2 terabps capacity single chip will be released. It uses 5 nanometer processing technology, and it supports 800 gig optics. And in 2026, 102.4 BPS capacity single chip will be released. and it uses 3-nanometer processing technology, and it support 1.6 terabps optics. This is Tomahawk. Intel, the Broadcom already announced the Tomahawk. Already announced a Tomahawk 4, and it is using. If we use a Tomahawk 4, then we can 64 by the 400 giga optics in or 256 port 100 giga in 2U. I'd like to explain the 800 giga and 1.6 terabps in less of time. 800 giga Ethernet, all next generation switching chip support 800 giga Ethernet using 8 by 100 giga SerDes. 800 giga Ethernet spec was completed in 2020, and 800 giga optics are available now. This is the first time our next generation optics are ready before our systems. And Broadcom already announced a Tomahawk 5, and it has a 51.2 terabps capacity, which using 5-nanometer technology. And if some vendor using this chipset, then the 64 port 800 giga or 128 port 400 giga into you. And also some vendor also release 800 giga platform, which is using 7-nanometer technology. Tomahawk 4 support 50 giga PAM4 technology, but also support 100 giga PAM4. So some vendor will release a 32 800 giga platform in 1U, but not to use 800 giga Ethernet. It uses 400 giga by 2. This is optics 800 giga optics module, and we have 800 Z12, FR8 and LR8, and but all DR8, and also we have 2 FR4 and 2 LR4, 2 DR4. Most of the 800 giga module will be used in breakout mode. 800 giga breakout application, 800 breakout support many use cases: aggregation, shuffle beta for to translate, tolerance, bigger radix. 800 giga to the dual 400 giga DR4, FR4, LR4, ER4 breakout, and also 800 giga DR4, DR8 breakout into the octal 100 giga DR. So most of the optics module already released 800 giga optics. So we can some vendor also demonstrating the system using 2 FR8 and DR8 optics. And this is later. This is sales of Ethernet transceivers to the top 5 cloud company. And 800 optics is ramping in the 2024, and in the 2026 it will be dominate over Ethernet transceiver in the top 5 cloud companies. That is 1.6 terabps. This is a programmer optics module roadmap, and OSFP 800 giga OSFP and 1.6 tera OSFP. It can support it will be used 200 giga PAM4, and it will be support 8 lane, and power requirement is up to the 30 watt. 102.4 terabps capacity switching chipset will be released in the 2026. If 1.6 tera OSPF use, the support 128 800 gig port were 256 400 gig port in the 2U. 1.6 tera OSFP optics module driving by the 3 nanometer 200 gig PAM4 SerDes ecosystem. All 5 nanometer chipset only support 100 gig PAM4. Primary use case are 2 by 800 gig and 4 by the 400 gig. OSFP 1600 spec is completed. Robust terminal environment for requirement for the 1.6 terabps optics up to 33 watt. Is there a way to get to the 1.6 terabps sooner? Then enter the OSFP XD. XD means the extra dense, which is newest MSA, 60 electron lane with 40 watt power environment. And 1.6 with 60 by the 100 and 3.2 tera with 60 by the 200. And doubles the front panel density versus 8 lane. This is OSFP and OSFP XD roadmap, and switching silicon the SerDes speed. Comparison the electronic interface vs optical lane speed. 100 lambda was 2 years ahead of the 100 gig switching SerDes, like 100 gig DR and FR. And the 200 gig lambda expected 2 years ahead of the 200 gig SerDes. This is 106 terabps roadmap. And at first, if switch using a 5 nanometer technology, and OSFP XD will be used, it supports 60 lane, 100 gig PAM4. And after that, the optical wavelength is support. Gearbox will be support 8 by the 200 gig. And it will be available in the 2024. And 3 nanometer technology switching chipset will be released 2026. Higher terminal environment requirement heat sink, integrated heat sink plus large surface area. So OSFP XD has the largest surface area, so it will be support up to the 40 watt power. This is a projection the transition from 400 gig to the 800 gig and 1.6 terabps. 800 gig and 1.6 terabps are expected to be 45% of our entire market in the 2026. 400 gig and below are expected to be 55% of entire market in the 2026. This is summary of my presentation. Rapid transition to the 800 gig and 1.6 terabps board. 800 gig and 1.6 optics offer significant benefit. Most of 800 gig 1.6 optics will be used breakout mode, and OSFP and OSFP XD are only be able pass to the 1.6 terabps. 200 gig lambda optics will start in ramping in the 2025. copper cage optics are not required for 51.2 tera or 102.4 terabps systems. This is a reference of my presentation. Presentation ended. Thank you for attention.
Thank you very much, Shishio-san. Any questions for future capacity or? No? Then I have a small gift for you. Thank you very much. ありがとうございました. So, what's next? We have Jan and Sander. They will talk about any cast, anywhere, anytime. So you have about 30 minutes, including Q&A. Was 10 minutes. Yes, that's a good point. So we can have more discussion. Was yours.
Thank you very much. Hi, everybody. My name is Jan George from Six Connect. I'm a VP with Six Connect Labs. This is Sander Stefan, also from Six Connect. And we are here to talk to you about how we started building Anycast. Basically, this is the documentary of how we were thinking, how we were solving problems, which kind of problems we ended up with, and how at the end found a way how to actively measure Anycast, because we knew that measuring Anycast globally is a hard problem. Okay, let's see if this works. Okay, Six Connect. It is a global company. So when I joined Six Connect, we had 9 DNS servers named NS1, NS2, NS3, NS4, NS5, NS6, and blah, 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 blah. And they were all around the world. And I was looking at that and I said, well, why we don't put this on Anycast, right? We have this beautiful technology, it's called Anycast. And
usually you start with a business case, you know, somebody
Exactly.
wants performance or Anycast. In our case, it was like, yeah, this sounds like a cool thing to do.
yeah, it's, you know, we're running a lab, so why not building a prototype of a node and see if that works? And together with Sander, we built a prototype in the lab and called Aaron and said, hey, Aaron, wouldn't it be cool if we have all those things Anycasted? And Aaron said, yes, great idea. So let's go. Let's build the Anycast network. So what we did was we built a prototype in the lab. We tested it. Then we started thinking about how to setting up measurements. I was looking at various measurement tools around the world, but nothing fitted really properly. I was looking at RIPE Atlas. You can do certain things with RIPE Atlas, but with Anycast, it's really not enough. And you will see later when I will be showing the measurement part. Then
but in this whole project, it wasn't like, okay, you know, we want a product, we make a plan. We just started, oh, this sounds like a cool idea. Let's spin up some nodes in some data centers and see what we can do. You know, how hard can it be?
Exactly. So then we started fine-tuning the prototype, did some more measurement, and announced around the world, done, right? This is supposed to be Anycast. We could ping over directly all our nodes who were alive around the world. They were announcing the Anycast prefixes, and that should be it, right? We are visible, yay! Not really. It doesn't work like that. It works in theory, but you know, in theory, there is no difference between theory and practice. In practice, there is a difference, and this is clearly the case. So first that we had to go through was software choices. So should we go with bind, node DNS, NSD, power DNS? Which one?
All of them.
All of them. Because, you know, if if there is a software bug in one of them, and of course, we automated the whole thing, the updates and the deployment around the world. And if there is a bug in one of them, when you upgrade, then your whole network is down. So we said, hey, let's put all of them. But then we skipped one, right? We are not running Power DNS anymore.
No, we started running out of memory at some point.
Yes, and Power DNS had some nasty bug with consuming more and more memory. There were some memory leaks. So now I think we are running bind, not an NSD, right? And we have a DNS dist in front. So DNS dist is distributing the DNS queries to all three backends in the back. Yes, I can see Jeff looking like, what? This is the most over-engineered Anycast node probably on the planet. But you know,
It gets worse, don't worry.
it gets worse. So we decided to do BERT2 for BGP routing because we can easily automate it. Sander is the master of Ansible scripting. I'm master of bash, sed, and awk scripting. So here we go, right? Okay.
We have had multiple occasions where I looked at the bash script and I was like, Jan, please step away from the keyboard.
Exactly. But I showed him the prototype in bash, sed, awk thingy, and he understood the concept and said, yeah, just throw this away. I will do it properly in the code. Yeah, but DNS dist provides scripting and monitoring. We have ZoneSync, the Python script to update zone files. Then Sander built a Damocles. That's basically a bash script to query DNS dist and kill BERT if there is a failure, if it doesn't respond with DNS. It's like, shuck. And we are managing it using Ansible, everything. So now if we are about to deploy a new POP somewhere, we just set up the VMs and let Ansible do all the thing.
Yeah, it's not a lot of work setting up a DNS server. You know, it's not that complicated, but say that there are like 50 or 100 steps that you have to take. And if you do this manually, you get about 90% right, and you forget 10%, but of course, every server you forget a different 10%. So, you know, and so at some point we were like, okay, if it's something you do once, you can do it manually, but we're running out quite a number of nodes here. So maybe we should just automate this because, yeah, we know where it's going.
Network admins tend to be lazy. We are a little bit lazy. Now we have like 13 nodes, and then the whole setup became a little bit not complex, but lots of things to configure. And then you start thinking, should I deploy a new node? That means like a couple of hours of working, manual working. I will rather do it next week. With Ansible automation, you go like, okay, let's spin up the VMs and let it configure itself. So we currently have clusters in Fremont, Ljubljana, Slovenia, and Apeldoorn in Netherlands. This is where we have our hardware. It's not a good spread, but it was a start to start testing a little bit. Now, which IP resources to use? How many IPv4, IPv6 prefixes? Which AS numbers? And at the end, we ended up using one AS and announcing 3 times 24 IPv4 addresses and 3 times /48 IPv6 addresses. Exactly.
You can never have too much redundancy, right?
Department of Redundancy Department. Okay, so now we have in each POP, we have 3 nodes. Each announces primary IPv4 plus primary IPv6 plus secondary IPv4 plus secondary IPv6 from the node next to it. And the second node also announces primary and secondary, and the third node announces primary and secondary from the first node. So whichever node we take down, the one of the other nodes take over the IP, and from the outside, it looks like nothing happened, right? Yeah, that's what I was just discussing. And method depends on the relationship to the routers. It's IBGP uses local pref, eBGP uses prepending, and that's how we juggle with the packets in between the nodes. Sander,
Yeah, so
to do this.
okay. So yeah, this is the setup we have. Every POP, we have 3 nodes. Every node has its own /24 v4 and /48 v6, and it's also the backup for the node to the left of it. So they're basically in a triangle, being backups for each other. So we can actually do maintenance on one of the nodes without causing any flaps in the routing table, because to the outside world, this POP is still routing all 3 /48s. So looking at Jeff, it's we are announcing a couple of more specifics, but we try not to cause any major updates. So yeah, this is the basic node. We actually have a 4th node for measurements. That's a bit that Jan will get into, because measuring Anycast and actually getting an idea of what are you doing, what is the effect of what you're doing, is much harder than it seems. So yeah, so we started with a couple of data centers. We had some servers, so hey, spin up a couple of VMs, why not? But it wasn't really working. Like there were black holes, there were routing problems, there was a lot of inefficiency. So yeah, we were like, okay, what's actually going on? So we need some measurements, we need some monitoring. Looking at the route views using RIPE Atlas, we could get some information. But especially the problem is if you're black holing traffic somewhere, you don't see it. You can monitor the traffic that gets to you, but it's very hard to monitor the traffic that doesn't reach you. So these were all very, very difficult problems to solve, actually. While we were thinking about this, we're like, well, you know, since we're busy anyway, why not just make our lives more complicated and add a few more nodes? So we used Vulture because they let us announce our own BGP prefixes. We deployed some VMs in Tokyo, added them, and then of course eat your own dog food. Run your 6Connect Labs domain on it, because well, if you want to know if it's working, shoot yourself in the foot, right? So this is how we started it. Now, of course, 6Connect is a IPAM company. We make IP address administration software, DNS administration, DHCP, stuff like that. So obviously, we were honor bound to actually use our own software for our own Anycast platform. You know, that's you can't bypass your own colleagues. They feel insulted. So from there, we push the zones. We're using Libre NMS to keep track of all the queries. We actually set up a whole bunch of Prometheus Grafana statistics to keep an eye on what's happening. So we could at least see the traffic that was arriving and how we were responding to it and what the performance was there. So the bit we were doing, we could see, but of course it's BGP. You don't know what everybody else is doing.
No, this speedometer was internal speedometer.
Yes, we could see from the inside, but not from the outside. And of course, we're running a lab. We're having crazy ideas. So we're starting with authoritative DNS. We actually had some customers that might want private recursive DNS because they have data centers all over the world and they just want to configure a static DNS server, and they don't want to use 888 or 999 or 111. So they were like, could you provide us with our own? So but that's something we may look at in the future. Of course, we also have a cloud service, like our software can be run on premises, but we also have a hosted version that we host for them. Can we actually Anycast that? Can we build a distributed database with distributed web front ends and actually use our Anycast as the front end load balancer for that? Can we do this for mail? Can we actually have do Anycast or mail services? So we started doing all kinds of crazy things. not necessarily because it's a good idea, but because we can and we're curious. So, and we actually have a really nice job that we're actually given the freedom to do all of this stuff. So, of course, not everything needs to be everywhere. Like I said, maybe we just use the Anycast nodes as a load balancer and then send the traffic to the nearest actual data center where the service is running, but also having a failover to a further away and therefore slower location in case there's an outage. So looking at different ways that we can actually provide a very stable service. Now, one of the problems is, unless we start announcing an insane amount of prefixes, all of them share fate. If our DNS server stops working, we have to pull the route, which means that also all the web and mill and other crazy stuff we're doing will also fail over to a different node, because it's all fate sharing. But you know, it's so far we're having a lot of fun playing with this. None of this is in production yet, obviously, but we are learning a lot. No, what the DNS is in production. None of the other crazy stuff is. Now, of course, if you're doing other stuff, maybe you want to do some DNS over TLS, HTTPS, stuff like that. People expect you to have certificates, so you want to use Let's Encrypt. But with Anycast, that gets really interesting, because you want to request a certificate. You have to prove that you're the owner, so you have to comply to the challenge. But you don't know where the Let's Encrypt validation is going to end up. So we try different things. Let's Encrypt actually, obviously you can use DNS, but if you're using HTTP, it actually honors redirects. So you could just redirect from node to node until it hits the node where the validation is. You can tunnel it to a central server and do the validation there. So we also built some solutions for this.
Yeah. So Trouble, you were doing the automation for Let's Encrypt. Maybe you should add also how do you do Anycast automation for the Let's Encrypt? That's how we just learned.
He says, watch this space. Hey, can I have the slides back? I'm not doing anything. Just press play, I guess. Thank you. So yeah, then we get to the thing like, are we actually globally visible? Where are the black holes? Because by now we're throwing a lot of engineering at this just to learn. But at some point, we really need to fix this routing issue. So why are people from the US sending their traffic to Japan and or to Amsterdam? Or where is all this stuff actually going? So we wanted monitoring for this. And we want to view this from the customer's perspective. So monitoring from our servers isn't going to help. We want to monitor from the world. And as you do, we actually ended up in Deventer, where our friend Remco van Mook lives. He's one of the RIPE-NCC board members. And we were just ranting at him a bit and drinking his whiskey, and you know how this goes. And he was like, well, you know, I'm actually starting a company to monitor exactly that. So over whiskey, we decided that we would be one of the pilot customers and try these tools to actually see what is going on, because we realized we were just running blind. So, Jan.
Yes. So while Remco was showing us what he's about to start, I was scratching my head and I was like, Remco, you know that this is exactly what we need to monitor and measure our Anycast network. And he was like, yeah, that's why I'm doing it. You know, we found more than one Anycast network on the planet, and we would like to build a tool to measure it. So when we deployed the nodes that we thought it would be great to have, and then started measuring it, this was the picture. And this is not a great picture. Red is not good. Red is bad. Green is good, right? So this is the software from Link State. It tells you a lot of stuff. It is querying your nodes from millions and millions of vantage points around the world, like every hour, every day. I don't know how often, but this is basically the first part of the dashboard that you can put together. You have success rate, average RTT. So this is sort of like the dashboard, how the whole network is performing. And then you have also all other types of measurements, like how many customers are going to which node and how big the RTT is for the majority of customers, and if there are more customers going to one node with a higher RTT or not. So this is where is the laser here? This is the laser. Yeah. So you see, this is good. This means low RTT, and for example, this is the number of people that is going to one of the nodes. But if you have big numbers here, this means that lots of people came to one of the nodes with a higher RTT, right? Then here, for example, we have the POP distribution. So how many users went to which POP? And there are many other things. So world map, we started with this.
Yeah, but by now we've actually expanded the number of nodes even further, obviously.
Yes. So we have a node in Fremont, in Miami. So we started with Fremont, Miami, Apeldoorn, Ljubljana, Tokyo, and Singapore. We started with this. And then obviously these are 6Connect data centers, and these are VMs on Vultr, where you can run BGP and announce your Anycast prefixes. But then we wanted to know who are the users of each POP and what's the latency. So for example, just follow the arrow. Fremont is basically using these people, but these people in Asia, they have a really long latency. And some people from South America. We saw also traffic from Oceania. Why is all this traffic ending up in Fremont? Magic of routing, right? Let's see Miami. These are people that is using Miami nodes. Why? Routing. South America is a little bit more disciplined. You can see the traffic to Brazil node is coming from South America, actually. Then we have Apeldoorn.
You can see that this one is connected to a big internet exchange. It attracts a lot of traffic.
Yeah. Then we have one in Ljubljana. It also attracts traffic from Oceania and Japan, despite the fact that there is a node in Japan for some reason. Singapore. See, why is traffic from North America going to Singapore? Routing, magic. Then we have Japan. This is a little bit more organized, like, around here. And then we have Oceania. It's like, it's our traffic. It doesn't go anywhere. Exactly. Don't you forget it. So, we got all this information from this nice tool. And then this is South Africa. We added a server, our own server, our own infrastructure to South Africa. And this is how all of a sudden the thing changed. So, but interestingly enough, this POP is also very well peered. Work online is a very well peered network. So the traffic to South Africa is coming from all around the world. It has a little bit higher RTT, but it's coming, right? So let's see how routing changes over time. So what is the dominant POP? For example, you have colors here. So this one is blue, light blue. So this one is attracting Canada and here and some places here. You see, this is all going to Fremont. Yeah, to Miami is going this part and nothing else. See, this one is attracting this part. Green is attracting also parts of Africa. Oceania is fine. So you see where your traffic is going. But then all of a sudden, on the next day, the routing changes completely. So this is the picture on the next day, right? And there is new pictures, like countries changes their preference for the POP. It's all magic of routing in Anycast.
And just to be clear, we didn't touch anything in the weeks that these pictures were taken.
Yeah.
We kept our hands off and just let the internet do its thing and just observed what happened.
So this is the RTT picture on the world, how the world sees our POPs. So this was before adding Brazil, Sydney, and JMB. This is how we originally envisioned that it would be quite okay to have these POPs and cover all the world. Boy, were we wrong. We were really, really wrong. Because when we started monitoring the whole thing, this is the picture that we got. See, we completely forgot about the southern hemisphere, right? And that's not fair. So we added Brazil and Sydney, and you see the picture completely changed. The RTT went down completely for the majority of the places. But then we figured out that our brothers in African continents are not reaching our POPs very, very, very efficiently. So we added Joburg. Look at that. It's nice and green, right? And this is why it's really, really important to measure your Anycast network if you happen to be building one, because if you don't, you never know how you are seen from the world, how you are reachable from the world. You need to measure it and then decide where to reinforce your presence. You see, this is, for example, a couple of weeks later, the whole thing changed, right? But you need to be prepared for all those changes and follow a little bit the topology. Present state, we are running all the Anycast DNS services for our own company, eating our own dog food. Then the war in Ukraine happened. René will talk about this tomorrow, I think, if he prepares the slides. But then we also part of Keep Ukraine Connected project to support Ukraine. And when we sent them a big pile of servers to reinforce their CCTLD inside Ukraine, we also told them, hey, why you don't put your .ua domain on our Anycast network for free? Because we want to support you, to help you for free. So now we are running .ua TLD on our Anycast network. And of course, Sander and I, when we are not traveling and talking to the community, we are building the distributed Anycasted email system. Let's see how that goes and what kind of problems that will cause. And also, as Sander mentioned, the designing Anycast IPAM. So those people who are using the instances on our cloud service, we will try to have that Anycasted and see what kind of different issues we can cause in that department. With that.
Thank you very much.
Thank you.
Questions, comment?
Rants, Rotten Tomatoes.
So Jeff, yeah, there's a mic, and please state your name before questioning.
Jeff Houston, Phoenix. Wow. Can everyone hear me? Because it sort of feels dead when I tap it, it works. Okay. The problem with the DNS and large packets is that once you get to a point greater than 1500 octets, you get into the whole issue of packet too big and ICMP. Now with V6, the issue is you can't fragment on the fly. So what needs to happen is that the ICMP 6 message needs to get back to the right point. How do you make sure that the reverse path aligns with the forward path in an Anycast network? Because if you have an answer, none of the other Anycast folk do.
We don't.
Right. So what do you do with the ICMP message about change the MTU for that destination?
Currently nothing.
So the real answer is you actually need to multicast that information back to all of your Anycast hosts, because you don't know what actual host needed to know that the MTU is for that destination smaller than normal. And so the standard trick is all ICMP messages are fanned out to everyone so that you're not basically driving into a black hole all the time, because reverse and forward are different with Anycast, or potentially so. Get the problem?
Challenge accepted.
Cool. One other thing too, might I add, the average AS path length on the internet is 5 ASs long. Anycast is always going to find it a challenge to actually optimize RTT, because you've only got 5 settings in your discrimination. We should have built a longer, stringier network and make it a whole lot easier, but we ended up building a short, fat, squat, dense network, which makes Anycast a really crude tool to do fine-grained RTT-based engineering.
Yeah, as you can see, the node in the Netherlands and the node in Joburg, both of those are well connected to internet exchanges with peers from all over the world. So, yeah.
And the other thing we get too is the large global transits look like one point. If you're close to them, whoever's close to them is close to everyone else, irrespective of RTT. And the service you really need is to avoid the really large transits and connect into finer grained infrastructure.
We actually had the problem with that when one of the first nodes was in Fremont, and that one was directly connected as a paying peer to the Hurricane Electric. And that one was attracting all the traffic from around the world.
You've encountered problem number 1, and we've all gone there.
Exactly.
Thank you.
But it was an experiment.
Thank you, Jeff. I have a comment to your comment. Multicasting the incoming ICMP to hold a node sounds like a good amplification. When you have 100 plus node, it to like multiplying the 100 ICMP message.
Yes. Look, this is not my idea. A number of other folk do it, and it's a case of the lesser of evils, because pumping answers in the DNS into a black hole gets no one anywhere. You know, you just time out, ask again, time out, and you never get an answer, even though you've got an Anycast network. And so somehow you need to circulate that information. Now, how else do you do it? No one knows. So
with V6, you could lower your MTU to 1280 and just make sure that the packet should get through everywhere.
I'm laughing hysterically as you say that.
Read that should in the RFC sense, yes.
Any other comment or questions? Good. If not, I have a small gift to you guys. Thank you very much.
Thank you very much.
Thank you very much. So this is the ending of Apops 2. And once again, we will have a lightning talk session Thursday afternoon. So if you have any idea or something to share, please submit your slide to the upload submission page. So that's all I have. Philip, do you have anything? Nope. Okay. So thank you very much. Now, coffee break.
so hard we try to be